So I'd like to start today's seminar. So today's speaker is Professor Ryotaro Tanaka at the Tokyo University of Science. So before start this seminar, I'd like to introduce him to you. Actually, Professor Tanaka has obtained his PhD degree from Kikitsuke Saito at Niigata University. He's working on the geometry of Banach spaces. So, for example, when we consider some equivalent norm in Euclidean space Rn, so we have a different properties, many properties about the finite dimensional Euclidean space, and if we equip some equivalent norms. Actually, he moves on to something more general, how to say, sister algebra and so on, so on. So this talk should be related to the properties such as reflexivity or separability and so on, so on. Okay. So please start. Thank you for coming to this seminar. So Professor Tanaka, please start.
Thank you for a kind introduction. First of all, I'd like to thank the organizers for kindly inviting me to speak here. Today, I talk about nonlinear classification of Banach spaces based on Birkhoff-James orthogonality. This talk is concerned with geometric nonlinear functional analysis or nonlinear geometry of Banach spaces. The main purpose of that area is to understand what and how structures determine Banach space properties without the aid of linearity, so nonlinear analysis. There are many striking results in nonlinear geometry. So for example, we have this theorem, the reflexivity, Radon-Nikodym property, and aspirantness are stable under Lipschitz homomorphism. Namely, if there exists a bi-Lipschitz bijection between Banach spaces X and Y, and if X is reflexive or has the Radon-Nikodym property or aspirant, then Y has the same property. So linearity is not needed here. And
excuse me. So what is aspirant property? Can you give me the definition? Yes, aspirantness.
Like differentiability, weak differentiability.
I see.
Okay, the dual property of Radon-Nikodym property.
I see. Thank you.
Okay. And the sequence space LP with P in this interval is determined by its uniform structure. So, namely, if there exists a uniformly bicontinuous bijection between LP and the Banach space X, then LP and X are isomorphic. So from this, we have this corollary. Classical sequence spaces LPs is classified by their uniform structure. So we don't need linearity here. So as seen above, main goals of geometric nonlinear function analysis are these 3 points: clarifying the stability of Banach space properties like reflexivities and the nonlinear isomorphisms, and finding essential structures that determine specific Banach spaces. So the uniform structure in LP. So providing classification theories based on nonlinear equivalencies. The theme of this talk belongs to this point, nonlinear classification of Banach spaces. So main tool in this talk is BirkhoffJames orthogonality. So in this talk, we focus on nonlinear classification based on Birkhoff-James or simply BJ orthogonality. So this orthogonality relation is a generalization of orthogonality in Banach spaces inspired by the nearest point characterization of the usual orthogonality. This definition is here given by Birkhoff in 1935. Let X be a Banach space over the scalar field K, and let X and Y be in X. Then X is BJ orthogonal to Y, denoted by this symbol, if this inequality holds for each scalar lambda. So from its definition, BJ orthogonality is closely related to geometric structure of Banach spaces. For example, if X is a unit vector and if X is BJ orthogonal to Y, then this set, so line, is tangent to the unit ball of X. This situation is generally explained by using support functionals for the unit ball. This theorem was given by James by 1947. Let X be a Banach space and let X and Y be in X. Then X is BJ orthogonal to Y if and only if there exists an F in the dual space of X satisfying these properties. So F supports the unit ball of X at X, and the Y is in the kernel of F. The basic properties of BJ orthogonality are as follows. So if X is BJ orthogonal to itself, then X is 0. This is called non-degeneracy. And X is BJ orthogonal to Y implies that for each scalars alpha and beta, alpha X is BJ orthogonal to beta Y. So this is homogeneity. However, meanwhile, as a bad property of BJ orthogonality, it is not symmetric in general. This theorem was given by Day and James independently. Let X be a Banach space. Suppose that the dimension of X is greater than or equal to 3. If BJ orthogonality is symmetric in X, that is, BJ orthogonality satisfies this property, then X is a Hilbert space. So BJ orthogonality is rarely symmetric in Banach spaces. The existing result strongly indicated that BJ orthogonality structure contains much information about geometric features of Banach spaces. So for example, smoothness and strict convexity are characterized in terms of BJ orthogonality. Hence, we anticipate that the large part of Banach space structure can be determined through the analysis on the behavior of BJ orthogonality. So based on this idea, we developed the theory of non-equivalence of Banach spaces based on Birkhoff-James orthogonality. The starting point of our study is the following theorem. So this theorem was given by Blank and Tanaka in 26. Now let X and Y be Banach spaces and let T be a linear mapping. If T preserves Birkhoff-James orthogonality in one direction, that is X pop BJ, Y implies that TX pop BJ, TY. Then T is a scalar multiple of an isometry. The real version was due to Koldovsky in 1993, and the proof given by Blank and Tanaka is valid both of the real and complex cases. So this is the starting point of our study. So as a consequence, we have the following result. Let X and Y be Banach spaces if there exists a linear bijection T from X into Y that preserves BJ orthogonality. Then X and Y are isometrically isomorphic. This means that the combination of linear and BJ orthogonality structures completely determines Banach spaces. Hence, as expected, a BJ orthogonality structure is fine enough to classify Banach spaces. So our next question is the following. What happens if the linearity is omitted in the preceding corollary? So what happens in nonlinear case? So to tackle this problem, we introduce a new nonlinear equivalence of Banach spaces. The definition, let X and Y be Banach spaces and let T be a mapping from X into Y. Then T is called a BJ orthogonality preserver if it is bijective and preserves the Birkhoff-James orthogonality in both directions. That is this equivalence for. So if there exists a BJ orthogonality preserver between X and Y, then we say that X and Y are BJ isomorphic. and write this symbol. BJ equivalence has the following properties. Let X and Y and Z be Banach spaces, then the following hold. So X is BJ isomorphic to itself. If X is BJ isomorphic to Y, then Y is BJ isomorphic to X. If X is BJ isomorphic to Y and Y is BJ isomorphic to Z, then X is BJ isomorphic to Z. And if X is a complex Banach space, and then X is BJ isomorphic to its complex conjugate. So anti-scalar multiple, having an anti-scalar multiple. So X and its complex conjugate is always BJ isomorphic. So we first consider the BJ classification in the finite dimensional case. The following is key. So lemma 1, let X be an n-dimensional Banach space. Then there exists a normalized basis x1 to xn for X, satisfying this property. So each vector that is orthogonal, BJ orthogonal to each element of the basis is 0. So this is like a complete orthonormal basis, so completeness of the basis. Using this, we have the following result. Let X and Y be Banach spaces such that X is BJ isomorphic to Y. If X is finite dimensional, then Y is also finite dimensional, and the dimensions of X and Y are the same. From this, we have this corollary. Let X and Y be Banach spaces such that X is BJ isomorphic to Y. Suppose that either X or Y is finite dimensional, then X and Y are isomorphic. So BJ isomorphic equivalence implies the isomorphic equivalence in the usual sense. So in finite dimensional case. The converse to the preceding corollary is false in general. Moreover, we will construct an example of a pair of two-dimensional Banach spaces X and Y such that X is BJ isomorphic to Y, but X is not isometrically isomorphic to Y. So BJ isomorphic equivalence is not equivalent to, not the same as the isometric isomorphic equivalence, so non-trivial. So this will be done in the context of Hilbert spaces and Radon planes. So consequently, the preceding corollary is sharp. Next, we consider smooth Banach spaces. Recall that Banach space X is smooth if for each non-zero X, its subdifferential near of X is a singleton. This is equivalent to the statement that the support functional for B of Bx, the unit ball of X, at each unit vector is unique. That is, the norm is Gato differential at non-zero vectors. In a smooth Banach space X, the singleton nu of X is identified with its unique element. A key sentence in the context of BJ orthogonality in smooth spaces is the following. So this lemma follows from James's characterization. Let X be a smooth Banach space and let Rx be this set for each X. Then Rx is equal to the kernel of nu of X for each non-zero X. So this follows from James's characterization using support functional. The set Rx is preserved and the BJ orthogonality preserves, regardless of the smoothness. So lemma 3, let X and Y be Banach spaces and let T be a BJ orthogonality preserver. Then the image of Rx and T is equal to Rtx for each X. In particular, if X and Y are smooth, then image of kernel of nu of x under T is equal to the kernel of nu of Tx for each non-zero x. So this lemma says that in a smooth Banach spaces, all support hyperplanes of the unit balls are preserved and the BJ orthogonality preserves. So this bridges the gap between linear and nonlinear arguments in the smooth setting. However, naturally, not all closed hyperplanes support the unit ball in general. So in this situation, the theory is developed by the assistance of the reflexivity. The theorem, let X and Y be smooth Banach spaces and let T be a BJ orthogonality preserver. If M is a reflexive subspace of X, then its image and the T is a closed subspace of Y. So to see this, it is sufficient to notice that M is intersection of the set of this form, satisfying this condition. Whenever M is a reflexive subspace of X. And this set is preserved under BJ orthogonality preserver. The image of this set is also a hyperplane in Y. The preceding theorem had the following corollary. Let X and Y be reflexive, smooth Banach spaces, and let T be a BJ orthogonality preserver, so reflexivity. But then M is a closed subspace of X if and only if its image and the T is a closed subspace of Y. This follows from the fact that each closed subspace of a reflexive Banach space is reflexive. Now we consider the classification of reflexive smooth Banach spaces. In this direction, we know powerful tools for utilizing the preceding corollary. So let X be a Banach space, then the lattice of all closed subspace of X is denoted by Cx. Based on the fundamental theorem of projective geometry, we can see that an isomorphism between Cx and Cy induces the bounded linear isomorphism. Namely, if we have these theorems, let X and Y be real Banach spaces if there exists an isomorphism between. So this means an order isomorphism. So there exists an order isomorphism between Cx and Cy, then X and Y are isomorphic. And in complex case, we have to assume.
Excuse me. So
Yes.
what was C of X? What was C of X? C, yes, in this, yes, this one, yes.
This is the lattice of all closed subspaces.
I see, thank you.
Okay, this is a lattice, and if we have an order isomorphism between the lattices of closed subspaces of X and Y, and then X and Y are isomorphic. So this is powerful truth. And in complex case, we need infinite dimensionality of X and Y. Let X and Y be complex infinite dimensional Banach spaces. If there exists an isomorphism between Cx and Cy, then X and Y are isomorphic, or X and the complex conjugate of Y are isomorphic. The infinite dimensionality here is used for proving the continuity of the induced mapping. So infinite dimensionality is needed here, cannot be omitted. So if X and Y are reflexive smooth Banach spaces, and if X and Y are BJ isomorphic, then there exists a BJ orthogonality preserver T from the definition. By corollary 2, T preserves closed subspaces of X and Y, and obviously the inclusion relation of them. So because this is a mapping, so thus we can define isomorphism rho from Cx into Cy onto Cy by this formula. Now the theorem in the previous slide apply. and we have the following result. So let X and Y be real, reflexive, smooth Banach spaces. If X and Y are BJ isomorphic, then they are isomorphic. And in complex case, we also have this theorem. Let X and Y be complex, reflexive, smooth Banach spaces. If X and Y are BJ isomorphic, then X is BJ isomorphic to Y or its complex conjugate. We remark that the finite dimensional case in complex version follows from corollary 1. So infinite dimensionality is not needed here. So these results are useful for classifying classical sequence space LP. So it is well known that LP spaces are reflexive and smooth for P with P in this interval, and each LP each pair of LPs are not isomorphic whenever P and Q are distinct. Moreover, in the complex case, we have that LP is isometrically isomorphic to its complex conjugate under this isomorphism. So this easy isomorphism gives this relation. Therefore, we obtain the following classification, nonlinear classification of the classical sequence spaces. So the family of LPs, P is in this interval, is classified by a Bija orthogonality structure. So new classification of LPs. So namely, if P and Q are distinct and in this interval, then LP is not Bija isomorphic to LQ. Before we leave this term, we see some recent developments. So we have developments, so good developments. So we have two theorems and more. So theorem 6, this was given by Ilishevich and Tansek in this year. So let X and Y be real smooth Banach spaces. So reflexivity is not assumed here. Suppose that the dimension of X is greater than or equal to 3, then X is BJ isomorphic to Y if and only if X is isometrically isomorphic to Y. So the conclusion is very strong. So nice improvements of my results. So in complex case, let X and Y be complex, infinite dimensional, smooth Banach spaces, and suppose that X or Y is reflexive. So reflexivity cannot be omitted in complex case. And then X is Bija isomorphic to Y if and only if X is isometrically isomorphic to Y or its complex conjugate. So we have these two very good, very nice improvements. Consequently, the BJ orthogonality structure is fine enough to determine Banach spaces by itself in the following cases. By the theorems in the previous slide, X and Y are real smooth Banach spaces and the dimension of X is greater than or equal to 3, or X and Y are complex infinite dimensional smooth Banach spaces. X is reflexive and X is isometrically isomorphic to its complex conjugate. So meanwhile, the non-smooth case is not so simple. So non-smooth case is very difficult. So it requires other tools and techniques. The next subject is about Hilbert spaces. This case is expected to have the simplest conclusion. That is true in the 3 or more dimensional case, but is not in the 2-dimensional case. So 2-dimensional case is complicated. So we first consider the easier part. Then the expected consequence is the following. Hilbert spaces are determined by their BJ orthogonality structure. In fact, this case is almost finished by the following theorem. So appear again. So let X be a Banach space. Suppose that the dimension of X is greater than or equal to 3. then X is a Hilbert space if and only if BJ orthogonality is symmetric in X. Since the symmetry of BJ orthogonality is stable under BJ equivalence, so a 3 or more dimensional Banach space is BJ equivalent to a Hilbert space only if it is itself a Hilbert space. So almost done. Therefore, it only remains to show that BJ equivalent Hilbert spaces have the same dimension. To see this, we know that BJ orthogonality is equivalent to the usual orthogonality in Hilbert spaces. Moreover, an orthogonal system E lambda in a Hilbert space is complete if and only if X is BJ orthogonal to E lambda for each lambda, implies that X is 0. So combining this with the fact that BJ orthogonality preserver T satisfies T0 equals 0, we have the following result. Let H be a Hilbert space and let X be a Banach space. Suppose that the dimension of H is greater than or equal to 3, then H is BJ isomorphic to X if and only if H is isometrically isomorphic to X. So namely, 3 or more dimensional Hilbert spaces are isometrically determined by the BJ orthogonality structure. Here we remark that this assumption, so the assumption on the dimension of H cannot be omitted, at least in the real case. So we next consider why this is so. The complexity in the two-dimensional case is caused by the variety of Radon planes. The definition of Radon planes here. Let X be a real two-dimensional Banach space, then X is called a Radon plane if BJ orthogonality is symmetric in X. In 3 or more dimensional case, the symmetry of BJ orthogonality rarely happens. So only in Hilbert spaces. However, in the two-dimensional case, we can construct various non-Hilbert Radon planes. Moreover, it turns out that smooth Radon planes cannot be classified by BJ equivalence by this theorem. Let X be a smooth Radon plane, then X is BJ isomorphic to L22, where L22 is the Euclidean 2 space. Thus, all smooth Radon planes have the same BJ orthogonality structure. A typical example of a non-Hilbert smooth Radon plane is as follows. So we have a concrete example. Example 1, suppose that P is in this interval and P and Q are conjugate. So P inverse plus Q inverse is equal to 1. Define a norm on R2 by this formula. So the first and the third quadrant, in the first and third quadrant, AB, the norm of AB is P norm. And the second and the fourth quadrant, then the norm is Q norm. Then this space is a non-Hilbert smooth Radon plane. So this space is called a James space, so classical space, and denoted by LPQ2. So as a consequence, in the two-dimensional case, Hilbert spaces are not determined by their BJ orthogonality structure. Moreover, the preceding example gives a pair of real Banach spaces X and Y, such that X and Y are BJ isomorphic, but not isometrically isomorphic. Hence, BJ equivalence is not trivial. In fact, this phenomenon occurs also in higher dimensions. So this phenomenon occurs also in higher dimensions. So we go to a non-smooth world. So analysis in the smooth setting finished almost in success. Our next subject is a theory, including non-smooth Banach spaces. then new tools and techniques are needed. In this section, we consider closure space structure in Banach spaces, which is stable under BJ equivalence. As an application, we give a complete BJ classification of C0 and LP spaces. Let X be a Banach space and let Rx be this set. We know that Rx is equal to X if and only if X is 0. Define a binary relation on X by declaring that X is less than or equal to Y if Rx is included in Ry. It is easy to see that this is a pre-order on X. So we borrow the notion of filters from the theory of posets definition. Let X be a Banach space and let F be a subset of X. Then F is a filter on X if it satisfies these conditions. So these conditions. So F is non-empty and F is upper closed. So if X is in F and if X is less than or equal to Y, then Y is also in F. And F is downward directed in this set. A filter F is said to be maximal if there exists, if there is no filter G containing F. We remark that each filter is automatically proper in X, provided that the dimension of X is greater than or equal to. So from this, by Zoll's lemma, we can always find a maximal filter containing a given filter. Hence, there is a sufficient amount of maximal filters on X. So we now introduce the geometric structure space of X. So this is a key item in the non-smooth world. So for maximal filter U on X, let IU be this set, the intersection of all Rx. Here, Rx is in U. So this set is equal to this set. So we can write this set by using the subdifferential of X. The geometric structure space Sx is defined by the set of all IU. Here, U is a maximal filter on X. And for each subset of Sx, define its closure by this formula. So this mapping has the following properties. Proposition, let X be a non-trivial Banach space, then the following hold. The closure of empty set is empty. And the closure include the original set, this set. And the closure of closure is closure. And taking closure is monotone. In other words, this mapping is a closure operator satisfying this condition. So the geometric structure space has the structure of closure space. In the following, the closure space Sx is said to be topologizable if this set, the set of all closed subsets in Sx, satisfies the axiom of closed sets. Naturally, not all Sx are topologizable. Theorem, let X be a non-trivial smooth Banach space, then Sx can be written by this. Moreover, if X is reflexive and the dimension of X is greater than or equal to 2, then Sx is not topologizable. So this is closure space, but not topological space. It turns out that the closure space Sx and its topologizability is preserved and the BJ orthogonality is preserved. Recall that mapping phi is said to be continuous if it satisfies this inclusion for each S. If P is bijective and bicontinuous, then it is called a homomorphism between Sx and Sy. Theorem. Let X and Y be Banach spaces such that X and Y are Bj isomorphic, then Sx and Sy are homomorphic as closure spaces. Moreover, Sx is topologizable, then Sy is also topologizable. So topologizability is also stable under Bj equivalence. So this result allows us to use geometric structure spaces for classifying Banach spaces by their Bj orthogonality structure. A milestone is found in spaces of continuous function. So theorem, let K be a locally compact Hausdorff space, then SC0K is topologizable. So this is topologizable case and is homomorphic to K. As a consequence, spaces of continuous functions are classified by their Bj orthogonality structure. So corollary, let K and L be locally compact Hausdorff spaces. And then C0K is Bj isomorphic to C0L if and only if they are isometrically isomorphic. So this is spaces of continuous functions vanish at infinity. So C0 is vanish at infinity. Since C0 and L infinity are isometrically isomorphic to spaces of continuous functions, the result in the previous slide apply. So it followed that C0 is not isomorphic, Bj isomorphic to LP, and is not Bj isomorphic to L infinity whenever P is in this interval, since SC0 and SL infinity are topologizable, but SLP is not. Moreover, C0 is not Bj isomorphic to L infinity by the preceding corollary. So this implies that isometric isomorphic. So thus, to classify C0 and LPs, what only remains is to show that L1 is not Bj isomorphic to these spaces. So first, we examine the topologizability of SL1, then we have the following result. So SL1 is not topologizable. Hence, L1 is not Bj isomorphic to C0 and L infinity. So our next aim is to show that L1 is not Bj isomorphic to LP whenever P is in this interval. To this end, we introduce a homogeneity property of Sx. The definition, let X be a Banach space, then Sx is Bj homogeneous if for each I and j in Sx, there exists a Bj orthogonality preserver T such that the image of I under T is j. This property is stable under Bj equivalence. So let X and Y be Banach spaces such that X and Y are Bj isomorphic. Then Sx is Bj homogeneous if and only if Sy is. So we have the following results. SL1 is Bj homogeneous. However, if P is in this interval and P is not equal to 2, then SLP is not Bj homogeneous. Therefore, LP is not Bj isomorphic to LP if this P is in this interval and P is not equal to 2, while P, the case of Hilbert space follows from the previous result. So as a summary, we have the following result. This family of classical sequence spaces is classified, completely classified by their Bj orthogonality structure. So this completes the first step of the study of nonlinear Bj classification of Banach spaces. The conclusion, the Bj orthogonality structure is fine enough to develop the theory of nonlinear classification. In many cases, Bj equivalence coincides with isometric equivalence. So Bj equivalence is rather strong. However, there are examples of pairs of Banach spaces X and Y that X and Y are Bj isomorphic, but not isometrically isomorphic. Even if the dimension of X is greater than or equal to 3, So to reveal an entire picture of BJ equivalence, a detailed research of BJ orthogonality structure in wider classes of Banach spaces are needed. This talk is based on these papers in this year. Thank you for your attention.
Okay, thank you for a nice talk. Is there any questions or comments? Do you have comments? I have a question. So,
Yeah.
for example, can you characterize some boundedness of property of some, how to say, a sequence linear operator such as Hardy transform or Hilbert transform for sequence LP spaces or something like this in terms of the BJ orthogonality? Or some
I think it is possible, but I don't know.
It should be possible, I guess. Thank you. Is there any other questions or comments?
I have a question.
Yes.
Okay, go ahead.
Yeah. So thanks for an interesting talk, and you showed us many results about LP spaces. Can you extend this theory to Orlick sequence spaces?
I think so. I think so. But not all. So. So not entirely, but partially we can, I think.
Are there any questions or comments?
Yeah, here I have also a question to Professor Tanaka.
Daniel.
Thank you for this interesting talk. So when you introduced the equivalence of BJ equivalent orthogonality, so you mentioned actually a very important inequality, which is also known as in accretivity of, for instance, or directional derivative. So in somehow your main results are related to accretive operators. Do you know any application to accretive operators of this theory?
Accretive operators? I don't know. I don't know the application. So.
But you know what I mean, yeah? Because exactly orthogonality, so this x plus lambda y is in norm is larger equal than the norm of x, is actually related to the directional derivative. And that's exactly the property that the resolvent operator is accretive. So in some sense, yeah. So that's the reason. So that there should be some relation, basically.
So there are some results on that topic, I think, but it is not related to the result in this study.
Yeah, I see.
Yes, but there is a relationship between such operators and BJ orthogonality.
So then,
So this BJ orthogonality is related to also semi-inner products. And through semi-inner products, the accretive operators and this notion relates.
So then there's another important question to this. So I mean, the LP and LQ spaces, they are reflexive. But when you are in L1, you lose exactly this property. So what can you still say about L1? And let's say large L1, not small L1.
Yes, good question. It is so difficult. I think difficult, but for BJ orthogonality, we can characterize. So I believe that large LP spaces can be characterized by a BJ orthogonality structure. but I could not prove it.
Okay.
Okay. Another question or comments? No? Okay, I still have another question. So you
Yes.
have been working on finite sequence spaces or infinite sequence spaces? Which one? So both enough?
Sorry?
So you have been working on finite sequence, how to say, sequence space over 1, 2, blah, 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 n, or a sequence space over n.
Infinite dimensional.
I see, I see.
Sequence spaces, infinite dimensional.
I understand. Thank you. And another small comment, and this is nothing to do with the talk, but your background can be seen from my house. I
Yes.
live in the next door. Maybe you have a guess. That's it.
Yeah.
Thank you. Sorry for this.
Thank you.
I have posted the invitation to the coffee break. So please, you're warmly invited. Everybody, Karina and Jungsi, you are all invited to the coffee break, which is now just following up after this talk. You don't have to wait until 5 p.m. or 4 p.m. Wherever you are, in which time zone. So please join us for a few minutes and to have a chat, personal chat with Professor Tanaka. And yeah.
Well, thank you once again, and I'll close this talk. Thank you for coming. So I finished. So see you next time. Bye.
Bye.
Thank you.
Bye.